Hello there, and welcome to the Sleepy Science Channel. Tonight, we enter the quiet and mysterious world of glaciers, the ancient rivers of ice that patiently and secretly shape our planet. These frozen giants carry memories of long-lost worlds, preserve traces of distant atmospheres, and carve entire landscapes with strength and determination. Within their deep blue layers rest stories that stretch far beyond human time, held in cold silence. Their presence is immense, yet calming. Light dances softly across their surfaces, and cold air pools at their edges. Beneath the ice, hidden worlds wait in darkness, untouched for thousands of years. Glaciers reshape mountains, feed rivers, and guide the slow pulse of water across Earth. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. Allow your body to soften and let your mind settle into stillness. Let's begin. Some glaciers hide entire mountain ranges beneath them. Beneath certain polar ice sheets, the surface looks deceptively smooth, a gently rolling plain of white that stretches to the horizon. Under that calm exterior, radar instruments have revealed rugged landscapes, with peaks, ridges, and deep basins completely buried in ice. These hidden mountains can rival well-known ranges in height and complexity, yet they have not seen open sky for an immense span of time. The ice above presses down with great force, filling valleys and smoothing sharp edges, but the stony skeleton of the range still shapes how the ice flows. Subtle humps on the surface can mirror towering peaks thousands of feet below. Meltwater streams may be guided along buried ridgelines, feeding secret lakes that never feel the warmth of the sun. In these concealed highlands, geology and glaciology intertwine, creating a world that modern instruments are only beginning to map in detail. There are glaciers so clear, they look like frozen glass. Most people think of glacier ice as white or softly blue, but in some rare places, the ice becomes astonishingly transparent. Over time, layers of snow are compacted so thoroughly that almost all the tiny air bubbles are squeezed out. The ice crystals grow larger and more uniform, scattering less light and allowing it to pass straight through. When such ice is exposed in a broken wall or along a polished surface, it can resemble a window into the heart of the glacier. Stones, trapped leaves, or small pockets of older, cloudier ice appear suspended in a clear medium, as if held in a glass sculpture. This clarity is not only beautiful, it tells scientists that the ice has experienced intense pressure and careful, orderly growth deep within the glacier. What began as fluffy, reflective snowflakes has transformed into a dense, luminous solid that reveals the patient work of time and pressure. Ancient air is trapped inside glacier ice. When snow falls on a cold landscape and never fully melts, each layer buries the one before it. As the snow is compressed into firn and then into solid ice, tiny pockets of atmosphere become sealed inside. These microscopic bubbles are time capsules. They hold the very air that once flowed around living creatures, over oceans and forests, through storms and quiet days long ago. By drilling deep into thick ice and bringing long cylinders of it back to the surface, researchers can sample those bubbles and measure the gases within. They can detect changes in carbon dioxide, methane, and other components that reveal how the climate has shifted through ages of ice and warmth. Each depth corresponds to a different moment in planetary history, stacked one upon another in a frozen archive. It is as if the glacier carries a layered record of breaths, storms, and seasons from worlds that no human ever saw. Glaciers move like slow rivers of solid ice. They appear frozen in place, yet their ice is always shifting, flowing outward under its own tremendous weight. Down at the crystal level, individual ice grains creep past one another, bending and deforming, so that the whole body of ice inches forward day after day. Sometimes the surface carries long, dark stripes of rock and dust, like currents traced across a frozen stream, revealing the paths that the ice has followed for years. Stakes placed on a glacier do not stay put. They drift downslope, quietly marking the passage of time in the landscape. Where the ice is thickest, or where meltwater lubricates the bed beneath, the motion can become surprisingly quick, enough to reshape valleys and push rocky debris far from its source. This movement is relentless. Even in the coldest darkness of winter nights, the ice keeps on going, carrying the memory of snowfalls that fell long before anyone was watching. Glaciers can flow uphill under the right conditions. At first, that sounds impossible, since gravity pulls everything downslope. The key is that ice behaves not only as a solid, but also as a material that responds to pressure differences in surprising ways. When a glacier is thick and heavy, the pressure at depth can drive ice from regions of high pressure to regions of lower pressure, even if that path leads slightly upward over a buried bump in the bedrock. From above, the surface might still appear to descend overall, yet along the base, ice can be forced up and over ridges before continuing its journey downhill. This process is guided by the total energy of the system, not just the steepness of the surface. Meltwater beneath the glacier can add to this effect by easing the ice over obstacles. In this way, these slow rivers of frozen water can quietly climb over buried hills as they continue their long migration. Some glaciers make deep, thunderous sounds when they shift. In cold, quiet valleys, the apparent stillness of the ice can suddenly be broken by booming echoes that roll across the landscape. These sounds often come from crevasses ripping open, or from blocks of ice grinding and slipping past each other under stress. The glacier is constantly adjusting to its own weight, temperature changes, and variations in how firmly it grips the rock beneath. When the stress builds beyond what the brittle upper ice can bear, it fractures, releasing energy as sound and vibration. Listeners might hear a cracking noise that grows into a rumble, then fades back into silence. Instruments placed on and inside the ice can detect many more of these events than human ears could catch, revealing a whole hidden symphony of snaps and groans. Each sound marks a moment when the glacier has rearranged itself, just a little, in response to the forces that drive it forward. Blue ice forms when glaciers compress snow for centuries. Fresh snow is bright and reflective, with countless tiny surfaces that scatter light in all directions. As snow is buried and compacted, the grains weld together into a denser mass, and many of the minute air pockets are squeezed away. Thick, pure ice absorbs the red and yellow paths of sunlight more strongly than the blue. The more distance light travels through this dense material, the more those warmer colors are stripped out, leaving a rich blue glow. In deep crevasses, along fractured cliffs of ice, or within compressed ice fields, this color can be striking, ranging from a soft turquoise to an intense sapphire. The shade tells a story about the purity, thickness, and internal structure of the ice. Where the blue appears most vivid, it can indicate long periods of quiet accumulation and compression, when snow quietly fell, settled, and slowly transformed into solid ice without frequent disturbance or melting. Glaciers carve valleys with incredible strength. As they move, they do not simply ride over the landscape, they grind into it. Rocks frozen into the base of the ice act like cutting tools, scraping and polishing the bedrock beneath. This abrasive action can deepen and widen existing river valleys, reshaping them into broad troughs with steep sides and relatively flat floors. In places where the glacier plucks large blocks from fractured cliffs, the valley walls can become jagged and dramatic. Over repeated cycles of advance and retreat, the combined effect of this erosion can be enormous. Entire valley systems can be transformed from narrow, winding channels into sweeping corridors framed by towering slopes. Lakes may form where the glacier has overdeepened parts of the valley floor, ready to fill with meltwater once the ice pulls back. Each curve of the landscape bears the imprint of this hidden sculpting, worn into stone by the steady work of moving ice. There are glaciers that float on the ocean. Where thick bodies of ice extend from land out over the sea, the front portions can become buoyant, forming ice shelves or floating tongues. The part still grounded on rock holds the upstream ice in place, while the floating section interacts directly with the ocean below. Seawater can flow into cavities under the shelf, melting it from beneath in patterns shaped by currents and water temperature. Above, large rifts can open in the floating ice, eventually leading to the release of huge tabular icebergs that drift away into open water. This floating extension affects how the glacier behind it flows, since the shelf acts somewhat like a brace that resists the pull of gravity on the inland ice. Changes in the thickness or extent of the floating portion can alter the speed at which ice from the interior reaches the sea, linking far inland snowfall to distant ocean environments. Some glaciers create their own winds. Air that rests over high, cold ice fields can become extremely dense and chilled. As night falls or clear skies allow heat to radiate away, that heavy air begins to slide down slope along the surface of the glacier. The flow gathers strength as it descends, forming a steady, often very cold wind known to locals in many glaciated regions. These winds can sweep through valleys, carrying fine snow and ice crystals, and creating distinct bands of colder air that influence local weather. They can clear clouds from certain slopes while piling them against others, shape snowdrifts, and affect how plants and animals cope with the harsh environment at the glacier margins. Instruments show that these air currents are guided not just by gravity, but by the contours of the ice, the surrounding topography, and the contrast between cold glacier surfaces and warmer ground below, a subtle beret. Climate engineered by frozen water, glaciers can hide volcanic heat below their surfaces. Beneath certain ice-covered regions, volcanic systems continue to pulse with energy even when the surface above appears silent and unmoving. The thick ice acts like a heavy blanket, trapping geothermal warmth below. That heat can melt the underside of the glacier, creating pockets of water that pool and flow in darkness. In some regions, entire networks of subglacial lakes form where volcanic warmth keeps the water liquid year-round. This hidden heat can alter the flow of the glacier by reducing friction along the bed, allowing the ice to slide more easily over bedrock. Steam and gases may rise through cracks in the ice, and in rare cases, the pressure can trigger explosive interactions between molten rock and meltwater. What appears as a calm, frozen plateau may be quietly shaped by geological forces working far beneath the surface, where fire persists under a world of ice. There are glaciers that surge forward suddenly. Most glaciers advance slowly, shifting their mass in a steady, controlled flow. Yet some undergo dramatic periods when their movement accelerates far beyond their usual pace. These surges can send the glacier racing forward many times faster than normal for months or years at a time. Deep within the ice, changes in pressure or the buildup of meltwater can alter the delicate balance that keeps the glacier moving at a predictable rate. Once that balance shifts, the ice begins to slide more freely over its bed. Crevasses open with startling speed, ice folds buckle and stretch, and entire sections of the glacier lurch ahead. When the surge ends, the glacier settles back into a slower rhythm, often leaving behind jumbled ridges of debris and newly carved channels. These sudden accelerations remain one of the most intriguing mysteries in glacial science, showing how rapidly ice can respond to changes within its hidden interior. Some glaciers glow with soft light from within. Under certain conditions, the interior of a glacier can appear to emit a gentle light. This glow is not produced by warmth or any biological process. Instead, it arises from the way dense, pure ice scatters and diffuses sunlight that enters through cracks, crevasses, or thin areas near the surface. Once inside, the light can travel surprising distances, bouncing between crystals and filtering into deeper layers. As it moves, the brighter wavelengths are gradually absorbed, leaving behind a cool blue radiance that seems to come from the ice itself. In overcast weather, the effect can be even stronger, since soft diffuse light spreads more evenly through the surface layers. The glow can reveal hidden textures and flowing bands of compressed snow laid down across ages. Observers who venture into safe ice caves sometimes describe the effect as standing within a lantern of frozen light, a still and silent world shaped entirely by ice. Glaciers hold most of Earth's fresh water. Although they may seem remote, these frozen bodies contain an immense share of the planet's accessible fresh water. The ice stores snowfalls that accumulated through countless winters, preserving them in layers that stretch deep below the surface. If all that stored water were released at once, it would raise global sea levels dramatically. This reserve is so large that even small changes in glacier mass can influence entire ocean basins and coastal regions. The water stored in ice eventually returns to the environment through melting, feeding rivers and lakes that support communities, ecosystems, and far-reaching watersheds. This slow release helps moderate seasonal flows in many regions. Glaciers serve as guardians of planetary moisture, keeping vast quantities of water locked away and stable through long periods of time. When they change, the balance of water across Earth changes with them, linking frozen heights to distant shores in ways both subtle and profound. Some glaciers move faster than you might expect. The common image of a glacier is that of a motionless block of ice. Yet some move at speeds that can be surprisingly quick for such massive bodies. Their surfaces may advance several feet in a single day, driven by internal deformation, basal sliding, and the steady addition of new snow at high elevations. When meltwater trickles downward and accumulates along the bed of the glacier, it can act as a lubricant that reduces friction, allowing the ice to glide more easily over the rock below. Warm summers, heavy snowfall, and internal structural changes can all increase motion. Crevasses widen faster, surface features migrate downslope, and chunks of ice break away from the front more frequently. Even though the speed is slow compared with flowing rivers, the movement is powerful enough to shift boulders, alter landscapes, and reshape entire valleys. These faster-moving glaciers demonstrate how dynamic ice can be when conditions align. There are glaciers that calve icebergs taller than buildings. At the ocean front of certain glacial systems, enormous blocks of ice crack away from towering walls and fall into the sea. These events, known as calving, can produce icebergs that rise far above the waterline. The process begins with tension building deep within the glacier as it flows outward toward the coast. Waves, tides, and undercutting by warmer seawater can weaken the base, while the weight of overlying ice stresses the upper sections. When the fracture finally opens, an immense block separates and crashes into the ocean with tremendous force. The splash may send waves rolling across the fjord, and the newly formed iceberg drifts away like a drifting island of ancient ice. Some contain intricate bands of old snowfalls compressed into patterns that reveal the history of the glacier. These enormous bergs are reminders of the sheer scale of frozen landscapes and the constant exchange between ice and sea. Glaciers leave behind giant sculpted landscapes. As ice advances and retreats through valleys and across plains, it carves, grinds, and shapes the terrain in unforgettable ways. The immense weight of the ice presses stones into the ground, gouging grooves and polishing bedrock until it gleams. Steep cliffs form where the glacier has plucked away blocks of rock, and broad depressions develop where it has deepened old river channels. When the ice pulls back, it leaves behind ridges of moraine, long arcs of stones and soil carried from distant places. Lakes fill hollows dug by the ice, and rolling hills appear where the glacier deposited mixed sediments. Over time, plants and animals colonize these new landscapes, creating ecosystems on ground that was once hidden beneath frozen layers. The marks of glacial work can last for ages, etched across continents and visible long after the ice itself has vanished. Some glaciers form mysterious meltwater tunnels under ice. Deep beneath the surface, intricate channels can form where meltwater gathers and begins to flow. Pressure from the overlying ice forces the water to carve winding paths through the glacier's base and interior. These tunnels can stretch for miles, sometimes carrying water with astonishing speed. Their shape and size change constantly as melting expands them or flowing ice closes them again. During warm seasons, the tunnels may connect with surface streams that plunge into crevasses and disappear into the glacier's depths. When explorers map these passageways using instruments and careful remote sensing, they discover spiraling chambers, narrow corridors, and unexpected intersections that reveal the complex plumbing of the glacier. Each tunnel tells a story about temperature, pressure, and the flow of water within a world of ice, where darkness hides processes that continue around the clock. Glaciers can create powerful outburst floods. Sometimes water builds up behind natural ice dams or in lakes trapped within glacier basins. When the pressure becomes too great, the barrier can give way, releasing a sudden and massive flood. These events send torrents of water, ice blocks, and sediment rushing downstream with immense force. The floodwaters can reshape valleys, sweep away vegetation, and change river courses within hours. The timing is often unpredictable, since the internal structure of a glacier can shift without warning. Researchers study patterns of melting and water accumulation to understand when such floods might occur, but the hidden nature of the water makes forecasting difficult. Once the rush has passed, new landscapes remain in its wake, marked by fresh channels and deposits of silt and stone. These floods are reminders of the power stored within frozen environments, where ice can hold back vast reservoirs until the moment of release. Some glaciers preserve ancient creatures perfectly. In extremely cold environments, animals that perish near glaciers can become locked within the ice before decay has a chance to begin. Over time, snowfall buries them deeper, insulating them from warmth and oxygen. The ice surrounds the remains and halts biological activity, preserving everything from skin and fur to internal organs. When the glacier eventually melts or shifts, these frozen beings may reappear near the surface, looking almost unchanged despite the passing of long ages. Scientists study such discoveries to understand ancient ecosystems, migration patterns, and environmental conditions that shaped the world in earlier times. The ice becomes a vault that holds these creatures in suspended stillness, connecting the present to distant eras when climates, landscapes, and living communities were vastly different. In this way, each preserved organism becomes a messenger from a forgotten chapter of life on Earth. There are glaciers that grind mountains into powder. As these massive bodies of ice move, they press stones into the bedrock beneath them with enormous force. Every inch of motion drags rocks across the ground like countless heavy blades scraping the surface. Larger fragments fracture and break into smaller pieces, and those smaller pieces are crushed again into even finer particles. Over long periods, this relentless grinding produces a soft, pale material often called rock flour. When meltwater carries this fine powder into lakes and rivers, it gives them a distinctive cloudy or turquoise appearance because the tiny particles scatter sunlight in a unique way. The entire process reveals just how powerful moving ice can be. Peaks that once towered high can be worn down, grain by grain. Valleys become smoother and deeper. Even the seemingly immovable strength of mountains is no match for the slow, unstoppable pressure of glacial ice. Some glaciers sing with high-pitched sounds. Within the cold walls of certain glaciers, delicate tones can rise and fade in the air. These high-pitched sounds come from a variety of subtle movements inside the ice. Tiny fractures opening and closing can release a brief, sharp note. Pressurized meltwater pushing through narrow channels can whistle softly. Even the shifting of ice crystals under changing temperature can produce faint vibrations that carry through the glacier. When conditions are just right, these small sources combine into a shimmering soundscape that locals sometimes describe as singing. Sensitive equipment placed on the surface can capture a rich chorus of pitches that human ears might not fully detect. Each tone reflects the physical state of the glacier, revealing changes in temperature, pressure, and internal flow. The effect is a reminder that glaciers are not silent at all. They hold a subtle acoustic life shaped entirely by movement within frozen walls. Glacial ice can be older than human civilization. Deep inside the thickest ice sheets, layers of snow from distant ages have been compressed into solid ice and preserved far beyond the span of recorded history. Each layer represents a winter that fell before cities rose, before written languages formed, before agriculture shaped human societies. The deeper one goes, the further back the record stretches, in some places reaching into times when the planet followed very different rhythms of temperature and climate. These ancient layers contain dust from volcanic eruptions, traces of distant storms, and even tiny bubbles of air that formed long before any modern human breathed. Scientists drill long cylinders of this ancient ice and examine them carefully to reconstruct environmental conditions from ages beyond memory. In this frozen archive, history is measured not in centuries, but in enormous sweeps of time, preserved with extraordinary clarity within the depths of the glacier. Some glaciers feed rivers that travel across continents. In many regions, meltwater that emerges from a glacier becomes the headwater of a river that flows for great distances. As the glacier melts during warmer seasons, clear, cold streams trickle from beneath the ice and gather strength as they move downslope. These streams combine to form rivers that cross plains, forests, and grasslands, supporting countless ecosystems along the way. Communities rely on this steady supply of water for agriculture, daily use, and hydropower. Even regions far downstream feel the influence of glacial melt, since the timing and volume of water can shape the rhythm of entire watersheds. Long after the meltwater leaves the shadow of the ice, it continues its journey across varied landscapes, linking distant environments to the high frozen source where the river was born. The glacier becomes part of a vast network that sustains life far from the cold world of its origin. There are glaciers hidden inside desert mountains. It may seem unlikely that ice can survive in regions known for heat and dryness, yet in certain high-altitude deserts, isolated glaciers persist in deep shadows where sunlight rarely reaches. These glaciers form in sheltered ravines or cirques where cold air sinks and remains trapped. Snowfall, though rare, can accumulate over time and slowly transform into ice if temperatures stay low enough. The surrounding landscape may be bare rock and sand, but within these protected pockets, frozen masses hold on through long periods of dryness. Their presence reveals how local topography and microclimates can preserve ice even in environments that seem too warm or arid for it to exist. These hidden glaciers offer scientists a chance to study how ice can survive in extreme conditions and how small, sheltered environments can maintain cold refuges even when the broader climate is harsh. Some glaciers create mirages on clear days. When sunlight strikes cold surfaces and meets pockets of warmer air rising from nearby ground, unusual distortions can appear above the ice. These shimmering visual effects bend light in ways that make distant shapes appear lifted or stretched. A ridge far away might look like it is floating, or a dark patch of rock may seem to ripple like water. On especially clear days, the contrast between cold air near the ice and warmer air from surrounding terrain can create layered temperature gradients that bend light dramatically. Travelers have sometimes mistaken these mirages for distant lakes or sudden cliffs, only to discover that the landscape shifts as they move. These optical illusions provide clues about the delicate balance of temperature and air density that forms above glaciers, revealing the invisible motions of the atmosphere that play out quietly over frozen ground. Glaciers can crack with tremendous vibrating roars. Although glaciers often appear solid and unchanging, the forces inside them build constantly. When the stress becomes too great for the brittle upper layers to withstand, a crack can open with explosive energy. A sound bursts outward as both noise and vibration, echoing along valley walls and resonating through the ice itself. These roars can start with a sharp snap, but grows into a rumbling growl before fading back into stillness. Instruments record the shaking as seismic signals that help researchers track how the glacier is moving and shifting. Some cracks open along the surface, creating deep crevasses. Others occur inside the glacier, unseen but powerful. Each event marks a moment when internal forces rearrange the structure of the ice. The memory of that sudden fracture remains in the glacier's layers, preserved in patterns that continue to evolve as the ice flows down slope. Some glaciers create rare frozen waterfalls. During certain cold periods, meltwater that usually flows freely from the glacier's surface or interior can freeze in mid-descent along steep cliffs. The result is a sheet or curtain of ice suspended where a waterfall once fell, capturing motion in still form. These crystal structures can grow thicker with each new freeze, forming delicate patterns that vary with temperature, sunlight, and wind. Some frozen waterfalls contain layers of blue or white ice that reveal changes in water flow, while others hold translucent columns shaped by splashes that solidified instantly. When temperatures warm again, the structure begins to melt from the inside or crack apart in large sections. These fleeting formations offer a rare glimpse into moments when flowing water and freezing air meet in perfect balance, preserving movement in the intricate sculpture of a frozen fall. There are glaciers that move on layers of slippery mud. Not all glaciers slide across solid bedrock. In some regions, a layer of soft, water-saturated sediment lies beneath the ice. This muddy foundation can deform easily, acting almost like a thick fluid that supports and transports the glacier above. As the ice pushes forward, the mud shifts and squishes, altering the speed and shape of the glacier's movement. This type of base allows even heavy ice to move more quickly than it would over a rough, rocky surface. The mud also traps and rearranges stones carried by the glacier, leaving behind unusual patterns of sediment once the ice retreats. Scientists study these muddy beds to understand how glaciers respond to changing water conditions and how soft ground influences the resilience and stability of entire ice systems. Glaciers can grow from a single persistent snow patch. In certain cold, sheltered locations, one patch of snow can survive summer after summer without melting away. Each winter brings new snowfall that adds to the old layer. Over time, the weight of these accumulated layers presses the lower snow into firn and eventually into ice. What began as a small patch becomes the seed of a miniature glacier. As it grows thicker, the mass becomes heavy enough to start creeping down slope. Small crevasses appear. Rocks fall onto the ice and become embedded. The patch transforms into a genuine glacier with its own flow, structure, and meltwater channels. This slow birth process shows how glaciers can arise from the simplest beginnings when conditions allow snow to outlast the warmth of summer. From a single persistent remnant of winter, an entire frozen system can emerge. Some glaciers hold clues to ancient climate shifts. Layer by layer, the snow that falls on a glacier becomes a record of the atmosphere that existed at the time it settled. Each winter leaves behind a sheet of snow with its own blend of dust, trapped air, and chemical signatures. Over long spans of time, these layers compress into ice that preserves an incredibly detailed timeline of environmental change. Scientists who study the deepest sections of glacier cores can detect past periods of warming and cooling, shifts in wind patterns, major volcanic eruptions, and even traces of vegetation carried from distant places. The thickness of each layer reveals how much snow fell in a particular year. The composition of tiny air bubbles tells how much carbon dioxide and methane were in the atmosphere. By examining these features, researchers can reconstruct climate patterns that stretch far beyond human memory. Glacier ice becomes a silent witness to Earth's shifting rhythms, preserving each turn in the planet's long environmental story. There are glaciers that form delicate needle ice structures. On the surfaces of some high-altitude glaciers, thin spires of ice can rise from the ground like tiny crystalline forests. These needle-shaped formations grow when strong sunlight warms the surface just enough to cause slight melting, followed by rapid freezing in cold air. The meltwater evaporates upward, leaving behind narrow ridges of ice that point toward the sky. Over time, these ridges can sharpen into intricate shapes that seem almost impossible for nature to produce. They form only under very specific conditions, where intense light meets extremely dry air and strong temperature gradients. Climbers sometimes find these fragile spikes difficult to cross, since the spires can be sharp enough to cut fabric or collapse unexpectedly beneath their weight. Their presence reveals how sunlight, wind, and cold interact in rare combinations to create formations as artistic as they are fleeting. Some glaciers stretch across multiple climate zones. Large glacier systems that originate high in mountain ranges or across polar plateaus often extend into regions with very different environmental conditions. At the top, snow drifts across ridges under frigid air, where accumulation far exceeds melting. As the ice flows downslope, it can pass into milder zones where temperatures rise and melting increases. Further down, the glacier may enter valleys with warmer summers and more variable weather, where meltwater streams cut channels across the ice. Yet the glacier remains one connected body, shaped by the contrasts between these zones. This creates striking differences in surface texture, color, and even motion along its length. The upper sections may be covered in fresh snow, while lower levels may reveal bare blue ice marked by debris bands. These gradients offer scientists a living laboratory for studying how a single glacier responds to entirely different climate influences from top to bottom. Glaciers can create their own lakes. As a glacier moves, it can carve deep hollows in the land beneath or leave behind large depressions once the ice retreats. Meltwater pools in these basins, forming lakes that owe their existence entirely to the glacier's earlier activity. Sometimes the lake forms while the glacier is still present, trapped behind natural ice or moraine dams. These glacial lakes can be vivid shades of turquoise or green because rock flour suspended in the water scatters sunlight in a distinctive way. In other cases, the lake appears only after the glacier melts back, filling the newly exposed landscape with fresh water. These features can grow, shrink, or change shape as melting patterns shift, They support unique ecosystems adapted to cold, mineral-rich water and provide important sources of fresh water for nearby communities. The landscape's shape becomes a reminder of the glacier's powerful sculpting long after the ice is gone. Some glaciers cause Earth's crust to rebound when they melt. The sheer weight of thick ice sheets compress the ground beneath them downward over thousands of years. When that weight is removed, the crust slowly rises again in a process known as isostatic rebound. This uplift continues long after the glacier has disappeared, sometimes for many centuries. Entire coastlines can rise, altering the shape of bays and inlets. Rivers may shift their courses as the land tilts upward. Ancient shorelines can be found far above modern sea level, marking previous positions of the land before rebound occurred. Scientists measure this ongoing rise using satellites and ground sensors, allowing them to track how the planet responds to long-term changes in ice cover. In this way, glaciers influence the shape of continents not only when they move, but also long after they melt, leaving behind a landscape that slowly rises to meet the sky once more. There are glaciers that trap entire forests beneath them. In some regions, advancing ice sheets have swept over valleys filled with trees and vegetation, burying them beneath tons of ice. The cold temperatures under the glacier preserve the organic material in remarkable condition. Roots, branches, bark, and even leaves can remain intact for long periods, protected from decay by the freezing environment. When the glacier melts or retreats, it may reveal these ancient forests, offering a glimpse into ecosystems that existed before the ice swept through. Scientists study the preserved wood to understand what species lived there, how the climate differed from today, and how landscapes changed as glaciers advanced. These fossilized forests provide an intimate view of a world that vanished under ice, yet left behind clues that help reconstruct the past with unusual clarity. Some glaciers creep through dense mountain passes. When a glacier encounters a narrow gap between mountains, the pressure of the ice behind it forces the mass into the constricted space. The ice adjusts by stretching, folding, and deforming to fit the shape of the terrain. Large crevasses may open as the glacier squeezes into the pass, while the sides can scrape along steep rock walls. This movement creates spectacular flow patterns that resemble frozen waves captured in mid-motion. Even though the passage may be tight and steep, the glacier continues forward, guided by gravity and the slow deformation of ice. Over time, the glacier widens the pass, smoothing sharp points and grinding away loose rock. These narrow channels bear the marks of the glacier's slow persistence, showing how frozen water can navigate and reshape even the most confined landscapes. Glaciers can split into multiple ice streams. Although a glacier may begin as a single mass of accumulated snow and ice, its flow can divide into separate branches as it moves across uneven terrain. Valleys, ridges, and variations in bedrock shape can direct the ice into distinct channels that act like independent rivers within the same glacier. Each stream may move at a different speed or follow a unique path depending on the slope, thickness, and underlying conditions. Where the streams rejoin, they may form dramatic folds or twisting patterns that reveal how the ice converged again. These divisions show the complexity of glacial motion and how sensitive the ice is to changes in topography. By studying how these ice streams behave, researchers gain insight into the forces that control glacial flow, from the smallest crevasse to entire frozen basins. Some glaciers create deep crevasses wide enough to swallow houses. The surface of a glacier is constantly under tension as the ice pulls, stretches, and bends while moving down slope. When the stress becomes too great, the brittle upper layer fractures into deep, narrow openings called crevasses. In large glaciers, some of these cracks can plunge down many stories, their depths disappearing into blue darkness. Their widths can grow so large that a person could walk through them if the edges were stable enough, though they rarely are. The sight of these immense fractures reveals the enormous forces acting inside the glacier. Snow bridges often conceal the openings, masking their true size beneath a thin cover of surface snow. The presence of such crevasses is a powerful reminder that glaciers are dynamic systems with immense internal tension, even when their surfaces appear smooth and calm. There are glaciers that flow all the way to the sea. In certain coastal regions, glaciers travel from high inland basins down through valleys and finally reach the ocean. These tidewater glaciers interact directly with seawater, forming dramatic ice cliffs at their fronts. As they continue to move, they release huge chunks of ice that break away and drift into the ocean as icebergs. The interface between glacier and sea is a place of constant change, where tides rise beneath the ice and waves carve patterns into its face. Seawater can flow into cavities under the glacier, melting it from below while cold air works on the upper surface. This dynamic environment influences both the glacier's speed and the conditions of nearby marine ecosystems. The flow of ice to the ocean becomes a powerful demonstration of how glaciers link high mountain snowfall to distant coastal waters in one continuous journey. Some glaciers create natural ice bridges. In certain places, meltwater streams carve tunnels through the lower layers of a glacier, hollowing out arches that remain standing even after the water has drained or frozen again. Over time, the roof of such a tunnel can harden into a smooth, curved span of ice that stretches from one side of a crevasse or valley wall to the other. These arches can be translucent or streaked with bands of blue and white, revealing layers of old snowfall pressed together by the weight above. Cold nights strengthen the structure, while warmer days can soften it, creating a shifting balance that changes the shape slightly over time. Though they may appear delicate, some of these bridges can withstand heavy loads because of the internal strength and density of the ice. Each formation is temporary, sculpted by water, light, and temperature into a natural bridge that eventually collapses as seasons and conditions change. Glaciers can flip over layers of ice, like pages in a book. As layers of snow accumulate, they compress into ice sheets stacked one upon another. When a glacier encounters an obstacle such as a buried ridge or a sudden change in slope, the lower ice can be forced upward. The intense pressure can fold the layers, twisting them until the older sections lie on top and the newer sections lie below. These overturned layers may appear along cliffs or crevasse walls as colorful stripes of blue, white, or gray. Each stripe represents a different time in the glacier's past. The folding process can occur slowly or during periods of rapid movement when the glacier flows faster than usual. Scientists read these layers to reconstruct the glacier's history, learning how it advanced and retreated long before modern observers took note. The ice becomes a physical record of its own journey, written in folds created by enormous subterranean force. Some glaciers hold hidden rivers rushing beneath them. Far beneath the quiet surface of a glacier, water can flow in powerful streams created by melting at the base. Pressure from the weight of the ice lowers the melting point, allowing liquid water to appear even in freezing temperatures. That water collects in channels that twist and branch through the darkness, sometimes forming networks that rival surface rivers in complexity. These subglacial rivers can move with surprising speed as gravity and pressure push the water through narrow passages. Some of the channels remain stable for long periods, while others shift or collapse as ice flows and refreezes. The water shapes the glacier from below, influencing flow speed by lifting sections of the ice slightly or by carving deeper grooves into the bedrock. Researchers use specialized sensors to map these hidden waterways, uncovering dynamic systems that remain invisible to anyone standing on the surface above. There are glaciers that grow even while surroundings warm. Although many glaciers shrink in warmer climates, a few unusual systems manage to grow despite rising temperatures in the regions around them. These glaciers exist where local conditions overshadow broader climate trends. Deep shade from steep cliffs, persistent cloud cover, or strong winds that blow drifting snow into certain basins can supply more snowfall than nearby melting can remove. In some cases, glaciers receive extra snow from avalanches that fall from surrounding peaks, adding layers faster than heat can melt them. These unusual accumulations allow the glacier to thicken and extend, even when surrounding valleys experience warmer seasons. Their behavior reminds scientists that glaciers respond not only to large-scale temperature, but also to local geography, snowfall patterns, and wind-driven redistribution of snow. Each example offers insight into the many factors that govern how glaciers evolve. Some glaciers store fallen meteorites. In certain polar deserts, meteorites that land on the ice become frozen into the upper layers of the glacier. As the ice slowly flows, wind-driven sublimation removes surface snow and ice from specific areas, causing the embedded meteorites to accumulate on exposed surfaces. Over thousands of years, these dark stones can gather in clusters on blue ice fields, where they are concentrated naturally by the movement of the glacier. Scientists search these locations to recover rocks that originated from asteroids, the Moon, and even Mars. The ice preserves them in remarkable condition, protecting them from weathering and contamination. Each meteorite offers clues about the early solar system, materials that formed planets, and processes that shaped worlds long before Earth's surface cooled. The glacier becomes a collector and curator of cosmic fragments, gathering pieces of distant space onto frozen ground. Glaciers can sculpt massive bowl-shaped cirques. At the head of many mountain glaciers lies a deep hollow carved by the repeated action of ice grinding against the rock. Over long periods, the glacier erodes the floor and walls of this space until it forms a steep-sided basin with a rounded floor. Snow accumulates in these protected hollows, feeding the growing glacier above. The cirque often remains shaded for much of the year, allowing ice to persist even when surrounding slopes lose their snow. Each cycle of freezing, thawing, and glacial abrasion deepens the basin further. When the glacier eventually retreats, the cirque remains as a permanent mark on the landscape. Many of these basins later fill with water, forming pristine lakes that reflect the cliffs around them. The cirque stands as a reminder of where the glacier was born and of the immense force it wielded in shaping its birthplace. Some glaciers grind boulders into smooth stones. As a glacier drags rocks across its bed, the stones grind against each other and against the underlying rock. Large boulders trapped in the base of the ice are worn down slowly. Edges soften, corners crumble. The stones become rounded and polished as the glacier continues its journey. In some regions, enormous fields of these smoothed stones lie scattered where the ice once passed, each one shaped by the glacier's relentless movement. These stones provide clues about how long the glacier remained in a particular area, how quickly it moved, and how much pressure it exerted. Their smooth surfaces reflect the immense force that flattened and polished them without shattering them completely. These polished stones are the glacier's footprints, left behind long after the ice has gone. There are glaciers that glow blue under moonlight. At night, when the sky is clear and the moon shines on the surface of dense ice, certain glaciers take on an otherworldly blue radiance. The light that enters the ice is scattered by its crystal structure, filtering out warmer colors and leaving behind soft shades of blue that appear to glow from within. This effect becomes most striking where the ice is pure and deeply compacted, such as along cliffs or within exposed crevasses. The glow shifts gently as the moon moves, revealing patterns that remain invisible during the day. The stillness and quiet of the night amplify the effect, creating a luminous landscape shaped entirely by ice, crystal, and faint light. This natural glow is not constant. It depends on the angle of the moon, the clarity of the sky, and the purity of the ice. Each appearance is unique to that moment. Some glaciers move in rhythmic pulses. Although glaciers generally move at steady rates, some display oscillations in their motion. These rhythmic pulses can occur daily, seasonally, or at irregular intervals. They may be driven by meltwater pressure building beneath the ice, by changes in snowfall at higher elevations, or by shifts in the internal structure of the glacier. When water pressure at the base increases, the glacier may slide more quickly over the bed. As the pressure drops, the movement slows again. This cycle can repeat, creating a pulse that scientists track with precision instruments. These oscillations reveal how sensitive glaciers are to subtle changes in water, temperature, and internal stress. The pulses can reshape patterns of crevasses, alter surface features, and influence how much ice reaches the glacier's front each season. These periodic surges highlight the living character of ice in motion. Glaciers can trap dust from distant continents. Fine airborne dust can travel astonishing distances on global winds before finally settling. When that dust falls onto glaciers, it becomes locked into the surface snow. Over time, new layers bury it deeper, and the dust becomes part of the glacier's stratigraphy. Each dusty layer provides a clue about conditions far beyond the reach of the glacier itself. Some layers contain volcanic ash from eruptions across the planet. Others contain particles from deserts thousands of miles away. As the glacier flows, these layers stretch and bend, preserving thin sheets of foreign material within the ice. Researchers analyze the composition of these particles to track long-range atmospheric movement, historical storm patterns, and major climate events. The glacier becomes a collector of signals from the wider world, storing them like pages in a global archive. Some glaciers form tall ice spires called penitentes. In extremely high altitude regions where the air is cold, dry, and thin, the surface of a glacier can develop tall, blade-like structures that stand in clustered groups. These formations grow when strong sunlight causes surface snow to sublimate rather than melt, turning directly into vapor. Tiny depressions in the snow deepen faster than flat areas, and over time, the surrounding surface is left standing in narrow peaks. These peaks grow taller as the sun continues to remove material from the hollows between them. The spires often point toward the sun, forming fields of pale blue blades that can rise higher than a person. Their edges can be sharp, and their shapes shift with each change in temperature and sunlight. These icy structures reveal how even in a frozen landscape, light and air can sculpt delicate formations that stand like frozen gardens on the glacier's surface. There are glaciers that create vast, muddy outwash plains. As meltwater flows from the front of a glacier, it carries with it a mixture of sand, silt, gravel, and stones that the ice has ground from the surrounding landscape. Over time, these materials spread across broad, flat regions, creating a braided network of channels that shift with each season. The plain grows layer by layer as fresh sediment settles during high melt periods. During warmer months, the watercourses weave through the area, depositing new material and rearranging the surface. The result is a landscape defined by constantly changing patterns of mud, gravel bars, and shallow streams. These outwash plains can stretch for great distances, linking the glacier to far downstream ecosystems. Their presence shows how glacial meltwater shapes terrain long after the ice has retreated, leaving behind sprawling zones created entirely by the steady release of sediment from the glacier's edge. Some glaciers carry massive boulders called erratics. Large stones that rest on glacier surfaces can be transported across long distances as the ice moves. These rocks may fall onto the glacier from surrounding cliffs, or be plucked from the bedrock below and lifted upward through ice flow. Once on the surface, they travel quietly, carried far from their original source. When the glacier melts, the stones are left behind in strange and often isolated positions, sometimes perched in open fields or on hillsides where no similar rock exists. Their size can be imposing, with some reaching the scale of small buildings. These misplaced giants tell the story of the glacier's path and the distance the ice traveled. Their unusual locations help researchers trace ancient glacial routes, revealing how ice once moved across landscapes now free of snow. Each boulder is a marker of past motion, delivered by the slow but relentless transport of ice. Glaciers can turn rocks into fine silt called rock flour. When glaciers drag stones across their beds, the grinding action reduces larger fragments into extremely fine particles. This powdery material is known as rock flour. Each grain is tiny, often far smaller than grains of sand. Meltwater streams carry rock flour away from the glacier, creating milky or turquoise water in lakes and rivers because the fine particles scatter incoming light. Over long periods, large quantities of this material accumulate in valleys and basins, forming fertile soil once plants colonize the area. Rock flour also reveals the intensity of glacial erosion, since its presence indicates that the ice has scraped and crushed rock beneath tremendous pressure. It is one of the most distinctive signatures of an active glacier, a direct result of ice shaping the ground it passes over grain by grain, moment by moment, across immense stretches of time. Some glaciers form vast layers of folded ice bands. Deep inside certain glaciers, alternating layers of snow from many different years compress into distinct bands of ice. These bands often vary slightly in color or clarity, reflecting changes in snowfall, temperature, or dust content. As the glacier flows over uneven terrain or bends around obstructions, the layers twist and fold like soft fabric under immense weight. Over time, these folds become graceful curves, loops, and arcs that can stretch for vast distances inside the glacier. When exposed along crevasse walls or polished ice cliffs, the folded layers create stunning patterns that resemble ribbons trapped in frozen motion. Scientists examine these folds to understand how the glacier once moved and how pressure changed the structure of the ice. The patterns serve as a visible memory of the glacier's shifting journey across its landscape. There are glaciers that collapse in towering icefalls. In steep mountain areas, glaciers can descend over abrupt drops or cliffs where the ice breaks apart into chaotic, towering masses. These icefalls resemble frozen waterfalls, with blocks and columns stacked at impossible angles. The ice fractures as it moves over the sudden slope change, creating deep crevasses, jagged ridges, and unstable towers. The constant motion prevents the formation from ever settling into a stable shape. New cracks appear frequently as the glacier flows, causing pieces to topple or split without warning. The sound of ice shifting echoes across the valley as the glacier navigates this dramatic transition. Though dangerous and unpredictable, these icefalls provide insight into how glaciers respond to steep terrain. They reveal the raw power of frozen water forced into motion by gravity, shaping a landscape of frozen cliffs and shattered ice. Some glaciers hide hidden caves sculpted by meltwater. Inside many glaciers, flowing meltwater carves, sinuous tunnels, and hollow chambers that wind deep into the frozen mass. These caves form when surface meltwater finds a crack or opening and plunges downward, melting channels as it flows. Over time, these channels widen into passages decorated with flowing patterns in the ice. Smooth walls shimmer with shades of blue, while ceilings arch in shapes molded by water swirling overhead. The structure of each cave evolves constantly as water flows, freezes, or changes course. Access to these caves can be limited and dangerous, yet they offer an extraordinary view into the heart of a glacier. Their presence shows how liquid water and ice interact, shaping hidden spaces within the glacier that remain unknown to anyone standing on the surface above. Glaciers can record volcanic eruptions within ice. When a volcano releases ash into the atmosphere, fine particles can travel great distances before settling. In glaciated regions, that ash becomes trapped in falling snow. Over time, these ash-laden layers compress into thin, dark lines inside the glacier. Each line marks a specific eruption, providing a precise record of volcanic activity that can be traced through time. Scientists drill into the glacier and analyze the ash to determine the strength and origin of past eruptions. These layers also reveal how atmospheric currents carried the ash across continents. The glacier preserves these events with remarkable accuracy, storing evidence of distant volcanoes in immaculate frozen layers. Each dark band becomes a timestamp, linking the history of fire to the slow accumulation of ice. Some glaciers move over lands that rise after ice melts. Under the immense weight of a glacier, land can be pressed downward. When the glacier retreats, the relieved ground begins to rise slowly. This uplift can continue for many centuries, reshaping coastlines, altering river paths, and changing the slope of entire regions. Glaciers that move over such rising land experience shifts in their flow because the landscape is changing beneath them. Slight tilts can influence how meltwater drains or how the glacier distributes its weight. These interactions reveal a dynamic relationship between ice and bedrock, where each affects the other across long spans of time. As the land rises, it carries with it the memory of the glacier's presence, showing how the ground itself responds to the ebb and flow of ice. There are glaciers that break apart in slow, spiraling patterns. Certain glaciers develop unusual rotational movements when ice flows unevenly across complex terrain. One side may move faster than the other, or subtle shifts in underlying rock may create curved pathways within the ice. Over time, the surface features of the glacier begin to twist, forming graceful spirals or arcs that drift downslope. Debris carried within the ice becomes arranged in looping stripes that reveal the rotational flow. These slow spirals form over many seasons and can continue evolving as the glacier changes shape. They demonstrate how sensitive glaciers are to tiny differences in slope, pressure, and inner structure. The patterns remain visible reminders of the glacier's internal choreography, a slow turning dance created by the movement of frozen water across shifting land. Some glaciers form stacked layers of ancient winters. Every winter adds a fresh blanket of snow to a glacier, and each summer compresses it beneath the weight of new snowfall. Over centuries, these layers transform into bands of ice that remain distinct from one another. Each band preserves tiny hints of the season in which it formed. Some contain faint dust from distant storms. Others hold clearer ice from particularly cold years, when snow compacted more efficiently. Viewed in cross-section, these layers appear as subtle stripes of differing brightness, texture, or clarity. They can stretch deep into the glacier, forming a chronological staircase of ancient winters stacked one upon another. Scientists can trace these bands back through tremendous spans of time to study snow patterns, atmospheric changes, and environmental shifts that took place long before recorded history. The glacier becomes a vast frozen archive, storing the passage of seasons with extraordinary precision. Glaciers can cool entire regions around them. A glacier's massive surface reflects sunlight and emits cold air that flows downslope. As this chilled air spreads into nearby valleys, It lowers local temperatures and creates microclimates that would not exist without the presence of the ice. Plants that normally grow at higher elevations can survive at lower levels thanks to the cooling effect. Animals adjust their habitats accordingly, relying on the glacier's influence to maintain stable conditions in the surrounding landscape. In some mountain regions, villages experience cooler summers because cold air pours from glacial basins each night. This cooling can even influence cloud formation and wind patterns, subtly shaping the weather. The glacier becomes not only a feature of the land, but also a quiet climate regulator. Its presence alters the environment in ways that ripple far beyond its frozen surface, linking the rhythm of melting and freezing to the daily life of entire valleys. Some glaciers have surfaces covered in dark algae. During warm periods, microscopic algae can grow in thin films on the surface of glacier ice. These organisms thrive in small pockets of meltwater, using sunlight to fuel their growth. The pigments they produce give the ice a darker appearance, ranging from pale grey to deep purple depending on the species. This darker surface absorbs more sunlight, causing the top layer of ice to melt faster. The algae spread in patterns that follow the flow of water across the glacier, creating streaks and patches that shift each season. Their presence reveals how even the most seemingly barren environments support life. Researchers study these algae to understand how biological processes influence melting rates and how microorganisms adapt to extreme conditions. The glacier becomes a living canvas marked by organisms that flourish in one of the coldest habitats on Earth. There are glaciers that slide on cushions of pressurized water. At the base of some glaciers, meltwater accumulates under such intense pressure that it acts as a thin, slippery layer between the ice and the rock beneath. This pressurized water reduces friction dramatically. As a result, the glacier can glide over the ground more easily than it would otherwise. The speed of the glacier changes depending on how much water is present and how rapidly it moves through subglacial channels. During warm seasons, increased meltwater can cause the glacier to surge forward slightly faster than usual. During colder periods, the water may freeze or drain away, slowing the motion again. This cushion of water acts like a hidden conveyor, guiding the glacier as it travels across the landscape. The process reveals how meltwater plays a crucial role in the behavior of glaciers, even when the ice above appears completely rigid and still. Some glaciers make cracking sounds that travel miles. Within certain glaciers, stress builds up as ice stretches, bends, or shifts over uneven terrain. When a fracture opens suddenly, the sound can echo across the mountains, amplified by cliffs and valleys. These cracking noises can be sharp, like splitting wood, or deep, like distant thunder. Even small changes in temperature can trigger these events as ice expands or contracts. Some of the fractures occur high on exposed slopes where sunlight warms the surface, while others form in deeper layers hidden from view. Sensitive instruments detect these vibrations from far away, revealing patterns of internal movement that help scientists understand how the glacier is evolving. The cracks travel outward in waves, carrying the message that the glacier is alive with motion. What seems silent from a distance is actually filled with sound, born from the immense forces shaping the ice. Glaciers can create sand dunes from ground rock. As glaciers grind rock into fine powder, they carry that material out through meltwater streams. When the water slows, the heavier grains settle first. Over time, winds pick up these loose sediments and shape them into dunes in nearby valleys or plains. These dunes can grow quite large, their shapes shifting under the influence of strong gusts that sweep down from the glacier. Although they resemble desert dunes, their origins lie in ice rather than heat. The sand often has a unique mineral composition that reflects the rock types the glacier has eroded. These formations reveal the extended reach of glacial activity. Even long after the ice has receded, the dunes remain as reminders of the glacier's grinding power and the sediment it created. The dunes become part of the changing landscape, shaped by wind, but born from the work of ice. Some glaciers form sharp ridges of ice called erites. When two glaciers occupy opposite sides of a mountain ridge, each one erodes its valley by plucking and grinding rock from the walls. As both glaciers deepen their valleys, the ridge between them becomes narrower and sharper. Over long periods, this ridge evolves into a dramatic spine of rock shaped by the tireless work of ice on both sides. The ridge may include jagged points and thin crests that rise high above the surrounding slopes. These arites stand as bold features in mountain landscapes, marking the line where two glaciers once shaped the terrain in parallel. Even after the glaciers retreat, the ridges remain prominent landmarks formed through careful sculpting by frozen water. Their form reveals the power of ice to carve mountains into elegant, angular shapes. There are glaciers that shape jagged mountain peaks. In regions where glaciers surround high summits, the combined forces of ice grinding on all sides can sharpen the peaks into striking pyramidal shapes. These pointed summits, often called horns, arise when multiple glaciers erode a mountain from different directions. Each glacier carves out a cirque basin, and where these basins meet, the remaining peak becomes narrower and steeper. Over time, frost, wind, and continued glacial erosion refine the shape even further. These dramatic peaks rise as remnants of rock left untouched by the deepest ice, yet shaped by its persistent influence. They reveal how glaciers not only carve valleys, but also sculpt mountains into distinctive forms that stand as icons of alpine scenery. Their sharp profiles reflect thousands of years of erosion focused around a single central point. Some glaciers leave behind giant crescent moraines. When glaciers push forward, they carry with them stones, soil, and debris scraped from the land. At the glacier's front, this material accumulates in ridges shaped by the outline of the ice. When the glacier retreats, these deposits remain as curved ridges called moraines. The shape of each moraine mirrors the glacier's former edge, often forming broad crescents that arc across the landscape. These ridges can be massive, containing layers of sediment transported from far upstream. Inside them lie stones of many sizes, from fine silt to boulders that once rode in or on the ice. By studying moraines, researchers can trace the glacier's former size and movement. Each crescent ridge becomes a frozen monument to the glacier's reach, marking where the ice once stood before it melted away. Glaciers can reflect sunlight in dazzling patterns. The surface of glacier ice often contains countless tiny crystals that scatter and refract light. When the sun strikes at the right angle, these crystals catch the light and send it across the surface in shimmering patterns. On windy days, drifting snow moves across the ice and sparkles like drifting stars. Crevasse walls reveal deeper shades of blue and white that glow when illuminated by sunlight. In some places, thin layers of surface meltwater act like mirrors, reflecting the sky in luminous patches. All these effects combine to create a dynamic and mesmerizing play of light across the glacier. Even small changes in cloud cover or sun angle shift the patterns instantly. The glacier becomes a living landscape of reflections that reveal its layered structure and crystalline beauty in motion. Some glaciers carve U-shaped valleys. When a glacier moves through a landscape, it modifies the original shape of the valley beneath it. A river-carved valley usually has a narrow floor and steep sloping sides. Once a glacier enters the same space, its massive weight presses downward and outward, widening the valley walls and deepening the center far beyond what flowing water could achieve. The glacier grinds the bedrock with embedded stones. smoothing and reshaping the sides while pushing debris forward. Over long spans of time, the valley becomes broad and flat at the bottom, framed by tall walls that curve in a gentle arc. This U-shaped form remains long after the glacier retreats, offering a clear signature of glacial passage. Lakes, meadows, and forests often grow within these wide valleys, flourishing in the terrain the glacier created. The shape itself becomes a permanent reminder of the immense forces once present, a memory etched into the land by slow-moving ice. There are glaciers that trap ancient pollen. As snow falls on a glacier, it occasionally brings tiny grains of pollen carried on high-altitude winds. These grains settle into the snow and later become buried under fresh layers. Over centuries, the pollen becomes sealed within the ice, preserved alongside dust, crystals, and bubbles of ancient air. Scientists can extract these trapped particles to learn what plants once thrived in distant regions. Some grains originate from forests that no longer exist in the same form, while others come from ecosystems that shifted with climate changes. Because pollen can survive for long periods in cold environments, it becomes a record of vegetation patterns long before written history. By studying these microscopic pieces of the past, researchers reconstruct the landscapes that surrounded ancient glaciated areas and track the movement of winds that carried the pollen across vast distances. The glacier becomes a quiet archivist, storing fragments of life from worlds long vanished. Some glaciers spill into fjords filled with marine life. Where a glacier reaches the coast, it may descend into a deep ocean inlet carved by earlier glacial activity. These fjords are often teeming with marine creatures that gather near nutrient-rich waters stirred by meltwater runoff. The glacier's front drops towering blocks of ice into the sea, creating floating platforms that shelter fish and invertebrates. As the ice melts, it releases minerals that nourish plankton, forming the base of a complex food web. The cold meltwater mixes with the salt water and creates layers of differing temperature and density that influence circulation patterns within the fjord. Seals, birds, and whales are frequently drawn to these icy environments, seeking food in waters shaped by the glacier's presence. The interplay of frozen and marine worlds forms a dynamic habitat where two very different realms meet. Each interaction between ice and sea becomes part of the larger ocean ecosystem connected to the glacier's steady flow. Glaciers can form massive plateaus of compressed ice. In some regions, glaciers accumulate so much snow that the upper sections spread outward rather than flowing rapidly downslope. The immense weight compresses layers of snow into a broad, elevated plateau that rises far above surrounding terrain. These ice fields can be incredibly thick, with smooth surfaces that stretch for many miles. Beneath the top layer, countless seasons of snowfall lie compressed into dense crystalline structures. The plateau acts as a reservoir that feeds multiple glaciers radiating outward from its edges. Weather patterns around these elevated surfaces can be unique, with cold air spilling down into valleys and strong winds sculpting intricate patterns across the ice. The stability of these plateaus depends on snowfall, temperature, and long-term climatic cycles. They stand as enormous frozen crowns atop mountain ranges, shaping the movement of ice far below them and influencing the surrounding climate through their sheer size and height. Some glaciers leave behind giant kettle lakes. When a glacier retreats, it can leave behind large blocks of ice, buried under layers of sediment. These isolated pieces melt slowly, creating depressions in the surrounding ground as they shrink. Over time, the hollows fill with water that collects from rain, groundwater, or nearby streams. The resulting lakes can be small or surprise the landscape with their immense size. Each lake forms in a distinct depression, shaped entirely by the melting of the buried iceberg. These basins often develop irregular shapes and varying depths, creating diverse habitats for plants and animals. Long after the glacier has vanished, the kettle lakes remain as markers of its presence. Their outlines reflect the random placement of the ice chunks left behind during the glacier's retreat, providing a clear example of how frozen remnants continue to shape the land. There are glaciers that carry entire layers of frozen ash. When volcanic eruptions send ash into the atmosphere, some of it eventually drifts down onto glaciated regions. Snowfall traps this ash within its layers, and over time, those layers become part of the glacier. The ash appears as dark stripes or bands within the ice, marking the season and event that produced the material. As the glacier flows, the ash layers bend, fold, and stretch into intricate patterns that trace the glacier's movement. Scientists use these layers to date volcanic events and track how atmospheric conditions transported the ash across long distances. Each stripe becomes a frozen snapshot of a moment in geologic history. The glacier preserves these moments with clarity, creating a record that links fire from deep within the Earth to the slow accumulation of ice on distant mountains. Some glaciers contain hidden networks of crystal ice. Within the depths of some glaciers, the pressure and temperature conditions cause ice crystals to grow into unique patterns that differ from surface layers. These crystals can interlock in complex arrangements that reflect the stress and flow within the glacier. When crevasses open or ice caves form, these networks become visible as shimmering patterns with varied textures and colors. The layers can shift from fine-grained to large faceted structures that catch light differently. These hidden zones reveal how ice adapts to the weight above it and the subtle movements of the glacier. Scientists examine these structures to understand how ice behaves under immense pressure, how crystals migrate and align, and how frozen water stores mechanical energy deep within its lattice. The glacier becomes an enormous laboratory of natural crystallography, shaped entirely by cold, pressure, and time. Glaciers can change sea levels around the world. When glaciers grow, they store vast quantities of water that would otherwise contribute to sea level. When they shrink, that stored water returns to the ocean. Even small changes in major glacial systems can influence coastlines across the planet. As more water enters the oceans, sea levels rise and reshape shorelines, flood low-lying areas, and affect currents. When glaciers expand during colder periods, sea levels drop, exposing land bridges that once connected continents. This exchange between ice and ocean has occurred repeatedly throughout Earth's history, altering migration routes, ecosystems, and the distribution of life. Modern measurements show how sensitive sea levels are to glacial changes, linking distant mountains and polar regions directly to the experience of coastal communities. The glacier's influence extends far beyond its frozen boundary, carrying global consequences with each gain or loss of ice. Some glaciers form ripple patterns on their surfaces. On certain glaciers, the surface becomes decorated with repeating ridges and troughs shaped by wind, meltwater, and the slow deformation of the ice. These ripple-like formations may form where cold winds sweep across the glacier consistently in one direction. They can also appear where meltwater drains in thin sheets and refreezes, creating parallel lines that drift down slope as the glacier moves. The texture of these ripples changes with season and weather, sometimes appearing crisp and clear, at other times softened by fresh snowfall. The patterns offer insight into the glacier's immediate environment and the forces acting on its surface. Each line marks the interaction of air, water, and ice at a scale fine enough to reveal subtle changes in the glacier's daily life. Seen across a large expanse, the ripples give the glacier a textured appearance that reflects its ongoing response to surrounding conditions. There are glaciers that grow in volcanic calderas. In rare locations, glaciers form inside the circular basins left by volcanic eruptions. These calderas often sit high above surrounding terrain and collect snow in deep sheltered depressions. The walls of the caldera protect the snow from strong winds, allowing it to accumulate year after year. As the layers build, they compress into ice that slowly begins to flow outward or inward, depending on the basin's shape. The combination of volcanic rock and frozen water creates a striking landscape, with warm geothermal areas sometimes sitting only a short distance from solid ice. These caldera glaciers offer researchers a unique environment where volcanic and glacial processes interact. The ice records changes in volcanic activity, while the rock walls influence the glacier's shape and temperature. The result is a frozen body shaped by heat and cold in an unusual partnership found only in these remarkable basins. Some glaciers shed ice that sparks with static energy. In extremely cold and dry conditions, pieces of ice that break away from a glacier can build up static charge as they scrape against surrounding surfaces. When these charged fragments tumble or collide, they may release faint sparks that dance across their edges. This effect is most noticeable when brittle surface layers crack apart suddenly, allowing freshly exposed ice to slide against the older material. The motion creates friction that lifts electrons from one surface and deposits them on another. In the still air of polar nights, the sparks can be visible as tiny flashes of pale light. They vanish quickly, yet each flash gives a glimpse of the hidden electrical processes active in frozen environments. Scientists studying these sparks gather clues about the insulating properties of glacial ice and the behavior of charge in extremely cold climates. Although brief, the sparks mark moments when frozen water carries energy usually associated with storms and dry deserts, revealing another layer of complexity in the life of a glacier. Glaciers can create hollow chambers that echo for distances. Deep beneath the surface, meltwater can carve large chambers where sound travels in unusual ways. The interior walls of these hollow spaces are smooth, polished by flowing water that has sculpted arcs and domes from the ice. When noise enters such a chamber, it bounces between the curved surfaces, amplifying and extending the sound. A single drop of water can create a series of echoes that drift through the darkness like distant bells. These chambers change shape constantly as freezing and melting adjust the thickness of the ice. Air pressure inside may rise and fall with the movement of outside weather, adding further resonance. Explorers who enter such spaces often describe the acoustic environment as surreal because even soft footsteps seem magnified. These echoing chambers show how water and ice can collaborate to produce natural sound stages hidden from the world above. Some glaciers leave behind stripes on bedrock. As a glacier passes over solid rock, stones frozen into its base scrape grooves into the surface, like blades pulled through clay. These grooves form long, straight stripes aligned with the direction of ice flow. Their spacing and depth depend on the size of the embedded rocks and the pressure exerted by the glacier. When the ice retreats, the bedrock remains etched with these parallel lines that reveal the path of the glacier and the force of its movement. Some grooves appear shallow and delicate, while others cut several inches deep. Scientists study the orientation of these stripes to reconstruct the motion of long-vanished glaciers and to understand how the landscape evolved under the weight of ancient ice. Each stripe is a lasting mark of contact between rock and frozen mass, carved by a glacier that continued moving long after the bedrock below recorded its passing. There are glaciers that form without ever snowing heavily. In certain cold, windswept regions, snowfall may be minimal, yet glaciers still develop. These glaciers grow not from frequent local snowstorms, but from snow transported by strong winds from distant areas. The winds sweep loose snow across open terrain and deposit it in sheltered basins where temperatures remain low enough for it to accumulate year after year. Even small amounts of snowfall can create a glacier if the temperature remains cold and the snow does not melt in summer. Over time, the captured snow compresses into firn and eventually into solid ice. The glacier then begins to move slowly downslope, shaped by gravity and internal deformation. These wind-fed glaciers demonstrate how ice can form under unexpected circumstances, supported by the steady gathering of snow from far away rather than from heavy local precipitation. Some glaciers move in curving S-shaped paths. Most glaciers flow in straightforward directions dictated by gravity, but some encounter irregular terrain that forces them into curved paths. When the glacier moves over uneven bedrock or through twisting valleys, the ice responds by bending and redirecting its flow. Over long distances, this can create graceful S-shaped patterns visible from above. The internal structure of the glacier reflects these curves as well. Bands of sediment and compressed ice follow the same winding pattern, revealing the glacier's changing direction over time. These curves show how sensitive glacial movement is to tiny variations in slope, pressure, and subglacial topography. They highlight the glacier's ability to navigate complex landscapes while maintaining steady forward motion. The resulting path becomes a frozen trace of the land's hidden contours, captured in the glacier's slowly shifting form. Glaciers can create hidden waterfalls beneath their ice. Where meltwater drains along steep slopes under a glacier, it can form cascading drops that behave like underground waterfalls. Although unseen, the flow echoes through tunnels and chambers carved by the constant movement of water. These falls can be powerful enough to shape new channels, sculpting the ice above them and the bedrock below. The sound of the falling water resonates within the confined space, producing deep rhythmic tones that travel through the ice. The falls change position as the glacier migrates, forming a dynamic system of shifting cascades hidden in darkness. Scientists use sensors to detect the vibrations created by these concealed waterfalls, learning how water moves within the glacier and how its flow affects the speed and stability of the ice. These secret cascades reveal the lively world that exists in the glacier's unseen interior. Some glaciers produce rare floating pancake ice. When circular pieces of thin ice fall near a glacier's outlet in cold moving water, they can bump against each other and spin gently. Their collisions create raised rims around the edges, giving each disc a rounded shape reminiscent of stacked pancakes. These formations occur when water remains cold enough to freeze, but also turbulent enough to shape the ice into circles. As more discs form, they cover the water's surface in floating clusters. Their soft edges rub together with every movement of the current, creating quiet murmurs that drift across the surface. The formation of pancake ice shows how glaciers influence nearby waterways by cooling them and supplying the right conditions for rare forms of ice to grow. The floating circles drift through the fjord or river, shaped by the interplay of temperature, motion, and the glacier's meltwater. There are glaciers that change color with the seasons. Throughout the year, the surface of a glacier can shift in appearance as light, temperature, and moisture vary. In winter, the ice often appears pale and powdery because new snow covers most of the surface. As spring arrives, the upper snow layers melt slightly and refreeze into smooth sheets that reflect more blue light. During summer, pockets of meltwater darken some areas while dust blown from surrounding land settles on the surface, giving certain sections a muted grey tone. Algae can also appear, adding subtle shades of green or purple in warm periods. When cooler temperatures return in autumn, the glacier brightens again as new snow softens the colors. These seasonal changes reveal the glacier's constant interaction with the atmosphere and its sensitivity to shifts in light and temperature. Its colors become a living indicator of conditions around it. Some glaciers contain ice so dense it sinks like stone. At great depths within a glacier, the pressure becomes intense enough to squeeze nearly all air bubbles out of the ice. Without trapped air, the ice becomes significantly denser than ordinary surface ice. When chunks of this deep ice break away near the front of the glacier and fall into water, they sink instead of floating. These submerged pieces descend slowly, shimmering as light refracts through the compact crystal structure. The formation of such dense ice takes long periods of compression under heavy loads of overlying snow. Its presence tells scientists that the glacier has maintained considerable thickness over extended periods. This type of ice demonstrates how frozen water can behave differently depending on pressure and environment, creating a material that looks ordinary at first glance, yet carries properties far removed from the ice found at the surface. Glaciers can produce meltwater that glows turquoise. When meltwater streams emerge from a glacier, they often carry microscopic particles of rock flour created by the glacier's grinding action. These tiny particles remain suspended in the water and scatter sunlight in a unique way. The shorter blue wavelengths of light are scattered more strongly, giving the water a vivid turquoise appearance. The effect becomes especially striking when the sky is clear and the sun is high, causing the water to shine with an almost luminous quality. Lakes fed by this meltwater can take on the same brilliant shade, creating colorful basins surrounded by rugged terrain. The glowing water reveals the glacier's influence long after the ice itself has melted, linking the color to the fine debris carried from deep within the frozen mass. The turquoise glow becomes a visual signature of glacial activity shaping the land and water. Some glaciers stretch across hundreds of miles. In certain polar regions, ice accumulates on such an immense scale that individual glaciers grow into sprawling bodies that cover vast distances. These giants extend from high interior plateaus all the way to distant coastlines, flowing steadily through valleys, across plains, and over buried mountain ranges. Their surfaces may look uniform from above, yet each section has its own rhythm of movement, shaped by snowfall, internal pressure, and changes in terrain. The thickness of these glaciers can vary greatly from one region to another, with deep interior sections holding layers of snow laid down far earlier than the ice found closer to the edges. Despite their enormous reach, they remain in constant motion, responding to shifting temperatures and the slow buildup of winter storms. Scientists who study these massive glaciers track subtle variations in their movement to understand how ice travels across such great distances. The scale of these frozen systems makes them among the most impressive features on Earth, storing memories of climates far older than any human record. There are glaciers that survive entire climate cycles. Throughout Earth's history, periods of warming and cooling have come and gone, altering coastlines, forests, and deserts. Yet certain glaciers endure through these cycles, shrinking during warmer phases but never vanishing completely. Their survival depends on a delicate balance of snowfall, shade, and temperature unique to their location. High mountain walls might shield them from direct sunlight, or cold winds may deliver more snow than surrounding areas receive. Over thousands of years, these glaciers witness dramatic environmental changes while maintaining a continuous presence. Their ice holds layered evidence of these ancient shifts, preserving traces of volcanic eruptions, dust storms, and atmospheric changes from each cycle. By studying these resilient glaciers, scientists can track climate patterns across timescales far beyond human observation. Their survival offers a reminder of how certain frozen landscapes can persist even as the world around them transforms again and again. Some glaciers leave behind polished rock, called glacial pavement. As a glacier moves across solid rock, stones embedded in its base scrape the surface with steady, grinding force. Over long periods, this abrasion can smooth the bedrock into a flat, polished expanse known as glacial pavement. The surface often shines with a subtle sheen, created by countless microscopic scratches aligned with the direction of the glacier's movement. Larger grooves may also appear where bigger stones dragged against the rock. When the glacier retreats, the polished surface remains as clear evidence of the ice that once passed over it. This type of erosion creates unique patterns on the land, showing how powerful and persistent glacial forces can be. Researchers examine these surfaces to reconstruct the ancient paths of glaciers and to understand how ice shaped the terrain. The pavement stands as a permanent marker of contact between rock and moving ice. Glaciers can create entire networks of braided rivers. When meltwater flows from a glacier, it often carries vast amounts of sediment from the ice and from the ground beneath. As this water emerges into open valleys, it spreads out and slows, causing the heavier particles to settle. The flow must then divide into multiple channels to navigate around the growing deposits. This process repeats continually as water rises and falls with daily and seasonal changes. The result is a shifting maze of rivers that weave around bars of gravel and sand, forming a braided pattern across the landscape. These channels join and separate repeatedly, creating a dynamic system that changes shape with each melt cycle. Plants and animals adapt to the fluctuating water levels, developing unique ecosystems along the riverbanks. These networks show how glaciers influence not only the land beneath them, but also the rivers that flow through distant plains. Some glaciers hold enormous frozen reservoirs. Deep within thick glacial systems, immense volumes of water become locked away as compacted ice. These frozen reserves can store moisture from countless winters, preserving it in layers that stretch far below the surface. The weight of the overlying ice compresses the lower layers into dense formations that hold this water in near-perfect stability for long spans of time. When the glacier melts or retreats, these reservoirs release their stored water gradually, feeding streams, lakes, and rivers that depend on this steady supply. Entire regions rely on these frozen reserves to balance seasonal water cycles. Scientists study the volume and rate of change within these glacial reservoirs to understand how water availability will shift in the future. The reservoirs remain silent, hidden within the glacier's depths, yet they sustain life far beyond the frozen environment itself. There are glaciers that collapse in cascades of ice blocks. On steep or unstable slopes, sections of a glacier can fracture into towering blocks that tumble forward in dramatic collapses. These events occur when internal stresses build faster than the glacier can adjust, causing large chunks of ice to break apart and cascade downhill. The falling blocks create thunderous crashes that echo through surrounding valleys. Each collapse reshapes the glacier's front, revealing fresh layers of ice that soon begin their own slow journey downslope. The process can be triggered by changes in temperature, meltwater buildup, or shifts in the glacier's weight distribution. Although short-lived, these cascades leave behind fields of shattered ice that record the moment of failure. Researchers study these collapse zones to understand the stability of fast-moving glaciers and to predict similar events in the future. Some glaciers generate their own local weather. Large glaciers influence air movement and temperature in ways that can create distinct weather conditions around them. As sunlight strikes the ice, heat is reflected rather than absorbed, causing the air above to remain cold. That dense cold air flows down the glacier, displacing warmer air in nearby valleys. This movement can trigger cloud formation, where the two air masses meet. Moisture carried on winds may condense along the glacier's edges, producing fog, light snow, or sudden shifts in wind direction. The glacier effectively becomes a natural climate engine, shaping conditions in its vicinity regardless of broader regional patterns. Plants and animals living near such glaciers experience these microclimates daily, adapting to temperatures and winds shaped by frozen water. These local weather patterns reveal how ice can influence not only the land, but also the atmosphere above it. Glaciers can trap microscopic life in suspended animation. Tiny organisms living in snow or meltwater can become trapped within glacial ice as new layers accumulate. Once enclosed, they enter a state where biological activity slows nearly to a halt. Low temperatures, limited oxygen, and lack of nutrients preserve them in remarkable condition for long periods of time. When the glacier melts or shifts, these microorganisms can re-emerge and resume activity as though little time has passed. Scientists study these revived organisms to understand how life adapts to extreme cold, low-energy environments and long-term isolation. Some microbes provide clues about early life on Earth, while others help researchers predict how life might survive on icy worlds elsewhere in the solar system. The glacier becomes a vault that stores microscopic communities in suspended stillness until the moment they are released again. Some glaciers form jagged crests called seracs. In steep and heavily fractured areas of a glacier, towering blocks of ice rise in chaotic formations known as seracs. These structures form where the glacier moves over sharp changes in slope, causing deep crevasses to open and intersect. The remaining columns of ice stand as irregular towers separated by narrow gaps. Their sides can be smooth or heavily sculpted by wind and meltwater. Seracs shift constantly as the glacier flows, making them unpredictable and unstable. Their jagged silhouettes create dramatic landscapes that show how the glacier responds to rapid deformation. The presence of seracs reveals areas where the ice is under intense stress, stretched and broken as it moves across rugged terrain. They offer a powerful reminder of the glacier's dynamic nature, even in places where the surface appears frozen and still. There are glaciers that march slowly across tundra landscapes. Some glaciers extend into low-lying tundra regions where the terrain is relatively flat. In these environments, the glacier advances slowly across ground covered in mosses, shrubs, and frozen soil. As it moves, the ice pushes aside or buries the vegetation, leaving behind a trail of disturbed earth. The glacier may override permafrost, influencing soil temperature and moisture patterns beneath its mass. Over time, the leading edge of the glacier can reshape the tundra, creating shallow depressions, ridges of pushed earth, and new drainage patterns. Wildlife living in the tundra adapts to the slow advance, shifting habitats as the ice encroaches. These glaciers demonstrate how frozen systems interact with delicate ecosystems far from mountainous terrain. Their movement across flat ground shows the versatility of glacial flow and its ability to transform landscapes one slow step at a time. Some glaciers carry layers of sediment that look like stripes. As glaciers move, they collect fine silt, sand, and small stones from the ground beneath, or from debris that falls onto their surfaces. Over time, these materials become trapped between seasonal layers of snow that later compress into ice. The result is a set of dark and light bands that run through the glacier like stripes. These layers stretch and bend as the glacier flows, recording its internal motion in graceful arcs. Some bands form from volcanic ash, others from dust storms, and others from rock fragments gathered along the glacier's margins. When crevasses open or cliffs of exposed ice appear, the stripes become visible as long lines that reveal the glacier's layered history. Scientists study these patterns to understand how much sediment the glacier has transported, how the ice has moved over time, and how environmental conditions shaped each distinct layer. Glaciers can bury entire landscapes under moving ice. A glacier's slow advance can completely cover valleys, forests, and fields in thick layers of ice. When the ice accumulates faster than it melts, it spreads outward, swallowing the surrounding land. Vegetation becomes trapped beneath the glacier's weight, preserved in cold darkness for centuries. Rivers may disappear under the ice, forced into new paths or sealed entirely. Hills become flattened, and natural landmarks vanish under a frozen sheet. This transformation alters the landscape not only during the glacier's expansion, but long after it retreats. Once the ice melts, the buried land re-emerges marked by erosion, compressed soil, and new drainage patterns. Lakes may form where the glacier once stood, and sediments left behind shape the topography for generations. The glacier reshapes everything it covers, creating a new world on the surface, and leaving ancient features hidden beneath its frozen reach. Some glaciers make trembling vibrations felt through bedrock. The movement of a glacier is not silent. Deep within the ice, grinding against stone and shifting under immense stress, vibrations travel through the bedrock below. These tremors can be too subtle for humans to notice, but strong enough for instruments to detect from great distances. When ice presses against a slope or rocks beneath the glacier crack under pressure, small seismic waves pulse outward. Meltwater rushing beneath the ice can also create rhythmic vibrations that resonate through the ground. These movements offer scientists valuable information about the glacier's internal dynamics and the conditions at its base. By listening to the faint tremors, researchers can map regions of fast flow, hidden cavities, and shifts in subglacial pressure. The glacier becomes a source of quiet seismic activity, marking its presence through subtle motions felt far beyond its visible boundaries. There are glaciers that form giant ice domes. Certain glacial systems accumulate so much snow and ice in their central regions, but the surface rises into vast rounded domes. These domes act like frozen summits, feeding ice outward in every direction. From above, they appear smooth and uniform, but within the dome, layers of ice flow slowly under their own weight, deforming and stretching as they move outward. The center often experiences extremely cold temperatures and constant compression, creating some of the densest ice found on Earth. Weather patterns around these massive domes are shaped by their height, with winds sweeping across their surfaces and cold air spilling down their sides into surrounding valleys. These ice domes function as engines that drive entire glacial systems, influencing how ice is distributed across hundreds of miles. They stand as monumental structures formed entirely from snowfall and time. Some glaciers leave behind long ridges of deposited sediment. As a glacier moves, it transports a mixture of ground rock, soil, and stones. When the glacier melts or pauses during its retreat, it drops this debris along its edges or at its front. Over many seasons, these deposits accumulate into elongated ridges called moraines. The ridges mark the glacier's former boundaries, preserving the shape of its advance and retreat. Some moraines stretch for great distances, curving gently across the land. They contain stones of many sizes, carried from distant mountains and released when the ice could no longer hold them. Plants eventually take root in the ridges, turning them into rolling hills that blend with the surrounding terrain. These deposits remain long after the glacier disappears, offering a map of its past movements and the path it once followed across the landscape. Glaciers can sculpt landforms that persist for ages. The relentless grinding, plucking, and shaping performed by glaciers leave behind distinct landforms that endure long after the ice melts. Valleys are deepened and widened. Cliffs become sharpened or smoothed. Depressions carved by ice fill with water to form lakes. Plateaus emerge where thick ice once pressed down on the land. Even isolated rocks perched on surfaces reveal how the glacier once carried them from distant sources. The combination of erosion and deposition creates a landscape of features that can last for thousands of years. These landforms tell the story of past glacial paths, marking where ice once flowed and how it altered the environment with its powerful movement. The marks remain like signatures etched into the land, offering a silent history that persists across ages. Some glaciers spread out into wide fans of ice. When a glacier flows from a narrow valley into a flatter region, the ice may fan outward, spreading like a river forming a delta. This broad expanse of ice is shaped by gravity and the topography beneath it. The glacier thins as it spreads, creating a gentle slope that extends across open terrain. Surface features shift as the glacier widens, forming patterns that radiate outward from the valley mouth. Meltwater streams branching from the glacier also fan across the landscape, distributing sediment in widening arcs. These fan-shaped glaciers show how ice responds when confinement disappears and space opens before it. Their shapes offer clues about underlying terrain and how the glacier transitions from steep highlands to open lowlands. There are glaciers that crack apart in glittering showers. In some regions, surface layers of glacier ice fracture into countless small pieces that scatter light like broken crystal. These glittering showers occur when brittle ice expands or contracts rapidly due to sudden changes in temperature. The cracking produces tiny shards that slide or tumble down the glacier's surface, catching sunlight as they move. In cold, clear conditions, the fragments can sparkle intensely, creating a momentary shimmer across the frozen slope. Each small crack is part of a larger pattern of stress release within the glacier, revealing how sensitive the surface can be to temperature variations. Though brief, these sparkling events add a dynamic visual beauty to the glacier, illustrating the constant adjustments occurring in its upper layers. Some glaciers move in secret beneath thick snow layers. In places where heavy snowfall blankets the glacier year after year, the movement of the ice beneath becomes hidden from view. The smooth white surface gives little hint of the crevasses, ridges, and streams flowing below. Yet the glacier continues its steady advance, carrying layers of ice and embedded debris forward. The snow above shifts gently as the glacier moves, forming subtle waves and depressions that reveal the faintest traces of the motion beneath. Scientists use ground-penetrating radar to study these concealed movements, uncovering a world of shifting ice and flowing water hidden below the thick cover. The glacier travels silently, unseen, shaping the land beneath while its presence appears calm and featureless from above. Glaciers can leave behind boulders carried from far away. As glaciers advance, they pick up large rocks from cliffs, valleys, and mountain slopes. These boulders become lodged within the ice or ride on its surface as the glacier moves. When the glacier melts or retreats, it drops these rocks in locations far from their original homes. The boulders may appear stranded on open plains, perched on ridges, or resting in meadows where no similar rocks exist. These transported stones, known as erratics, reveal the reach and direction of ancient glaciers. Their size and placement tell the story of how the ice once flowed and how powerful its movement must have been to carry such massive objects. Even centuries after the glacier disappears, these far-traveled boulders remain as unmistakable evidence of its past journey. As we drift to the end of this quiet journey, take a moment to feel the stillness that glaciers leave behind. These frozen worlds move slowly, yet the stories they carry are immense. They shape mountains, guide rivers, cradle ancient winters, and hold memories far older than anything written. Even now, long after our exploration has paused, the ice continues its patient work, shifting grain by grain and layer by layer in the deep calm of the natural world. You have wandered through places touched by cold light and deep time, through frozen valleys and hidden chambers, through landscapes shaped by quiet persistence. Glaciers remind us that the world is always changing, even when the change is too slow to see. They show us the beauty of patience, the power of subtle forces, and the way small moments build into vast histories. If you enjoyed this slow and gentle journey, I invite you to like, subscribe, or share the thought below. It helps others find their way here too, one sleepy soul at a time. For now, let the weight of the day slip away. Breathe softly. Let your mind settle like snow on calm ice. Let your thoughts drift wherever they wish to go, carried by the quiet movements of the world we have just explored. Good night.